We'll now introduce another method for solving nonlinear equations, and this is known as the Newton-Raphson method. As the name implies, this was developed by Isaac Newton and Joseph Raphson, and this is another iterative method for solving nonlinear equations. As a side note, since we're in the middle of a pandemic and we're talking about Newton's method here, I think I have to share the story about Isaac Newton. So one day during this really long stay at home, and I got bored and wanted to read about the life of Isaac Newton. So he actually had a quite impressive life where his mother actually wanted him to become a farmer. But his teachers actually persuaded his mother to send him back to school. So he was able to go back to school and he was admitted to Cambridge University. And after he completed his BA degree at Cambridge University in 1665, I'm reading from here, the university temporarily closed as a precaution against the Great Plague. So there was a pandemic in his era as well, and he had to stay at home at his original home in Woolthorpe and work over there. So the Wikipedia page says that Newton's private studies at his home in Woolthorpe over the subsequent 2 years saw the development of his theories of calculus, optics, and the law of gravitation. This made me feel really bad about myself because I don't know about you guys, but I think I'm also at home during a pandemic, but I'm just dying slowly. Hopefully one of you guys become the Newton of our generation. All right, so let's go back to Newton-Raphson. Let's recall the first order Taylor approximation given by the following form, where f of x plus h is approximately equal to fx plus f prime of x times h. In our context, given a current guess of the solution xk that is reasonably close to the true solution x star, we have that fx star is equal to fxk plus some h, and that's approximately f of xk plus f prime of xk times h. This is a linear function of h for approximating f near xk. Instead of solving the original nonlinear equation, fx star equals 0, the Newton-Raphson method solves for h such that this Taylor approximation is equal to 0. You can see that the solution of h is negative fxk divided by f prime of xk. Thus, the next approximation of x star is given by xk plus 1, that is equal to the current xk plus h. Plugging in the solution of h, this is going to be xk minus fxk divided by f prime of xk. So here are the specific procedures. The Newton-Raphson method begins with an initial guess x0 that is reasonably close to the true value x star. At each subsequent iteration, k equals 0, 1, 2, etc., in step 1, we evaluate f and f prime at the current xk. And then we will update the value of xk in the next iteration by xk minus this ratio over here. This is repeated until reaching the maximum number of iterations, or until fxk is sufficiently close to 0. So here's a graph for illustrating this. This is the initial iteration where we have an initial guess x0. And you can see that the true solution is somewhere near here where the curve intersects with the x-axis. So at the current x0, we calculate fx0 as well as f prime 0. So this tangent line has slope that is equal to f prime of x0. And then we look for where this tangent line intersects with the x-axis. In other words, when this tangent straight line approximation is equal to 0. And we can see that it intersects with the x-axis at this point, so the pink point over here. And that is going to be our next x, which is x1. In the next iteration, we repeat the same thing. For x1, we calculate fx1 as well as f prime of x1. We find where the tangent line intersects with the x-axis, and the intersection point is our next guess, which is x2. And as you can see, this gets closer and closer to the solution over here. Let's try to use the Newton's method to solve for the earlier equation, where Fy, which is the quadratic equation, is equal to 0. Because the Newton-Raphson method involves the derivative, the first derivative, f prime, so we need to first calculate that. We can see that in this case, the f prime of y is given by 2y plus 2a divided by n minus 1, where a and n are pre-specified constants. So let's create a function for computing f prime from y, a, and n. So here's the function, and we call it f prime. It returns the f prime y given over here. We will start with an initial guess x0 equals 50. And again, let's assume that a is equal to 0.5 and n is equal to 20. So here's the code for Newton-Raphson. We begin with initializing the x's and the fx. And we also initialize the iteration number and set the tolerance level. Next, we can begin iterating the Newton-Raphson algorithm until 1000 iterations has reached, or until the absolute value of fxk is less than or equal to our tolerance. So while the absolute value of fx at the current x is still greater than epsilon, and the iteration number is still below 1000, we will first evaluate x prime at the current xk. So we use the function f prime to do this, plug in the current x value and the a and n. And then, based on fx and f prime of x, we will update x to xk plus 1. This is given by the current x, xk, minus the ratio between fx and fp, so f prime. We will also increment the iteration number by 1. After doing this and obtaining the new x value, we will update the fx by evaluating the f function again at the new x. And we will store the results in a vector. So we will store all of the x's, so all of our guesses, until the algorithm terminates. So here are the results of solving that quadratic equation using Newton's method. The number of iterations was equal to 7, and the solution in the last iteration, which is given by the current x value, is around 4.19 again. The corresponding fx is again really close to 0. And here is the xk values at each k, so the x guesses at each iteration. We started with 50, and then you can see that in as little as 7 iterations, it converged to something that's really close to the true value. One thing you might notice here, comparing to the iteration number in the bisection case, which was 21, is that the Newton-Raphson method converged faster than bisection. In fact, the rate of convergence for the Newton's method is r equals 2 if f has just a single root. In other words, in the case that the function only has an unique root, the Newton's method converges quadratically.